In the last unit, we saw that for gases, pressures, volumes, and moles are proportional to the reaction coefficients. In this unit, we'll be extending this skill to solids and liquids in addition to gases, as moles are always proportional to the reaction coefficients. There are a number of ways to make stoichiometric calculations in order to relate grams of reactants to grams of product that would be formed. I actually got this particular method from a former student who wanted a more concise way of organizing the information. I realized that this method is more closely related to how I've been doing the calculations myself, so I have been teaching students to use stoichiometry charts ever since. So what you do with stoichiometry charts, the first thing you want to do is set up the x's thing like we were doing with gas stoichiometry. So here we have 2 aluminum is reacting with 1 iron 3 oxide to form aluminum oxide and 2 iron. So just using the coefficients, that's going to be a 2x, that's a 1x, aluminum oxide is a 1x, and iron is a 2x. The next thing we're going to do is we're going to do the easy step, which is to figure out the moles of everything. So down here we have that 1x is 0.051, so that means the iron oxide, which is also a 1x, will also be 0.051. And then 2x is just going to be 2 times as much, so this would be 0.102. And the iron metal will also be 0.102. All right, now that we've done the easy part, you need to fill in your molar mass, or GFM, for each thing so you can find the grams. Now, the big thing that I found that students have trouble with is they start using the coefficients again when they do GFM. Molar mass is just the compound itself. It doesn't have those reaction coefficients. So as I tell my students, it's just the little numbers. So in the case of iron, it would just be 55.845. And aluminum would be 26.982. Now we have to figure out the molar mass of iron 3 oxide. So that would be 2 times the molar mass of iron plus 3 times the molar mass of oxygen, and you get a value of 159.688. Oops. Do the same thing for the aluminum oxide. So it's going to be 2 times the molar mass of aluminum plus 3 times the molar mass of oxygen, and it ends up being 101.962. So now if we want to find grams, remember Moletown, if you have moles and you have the GFM, you're just going to multiply, and that will give you the grams. So we do 0.051 times 159.688, and we get that this will form require 8.14 grams of iron oxide. Do the same thing for the aluminum oxide. Just multiply the moles times the molar mass, and we get that this is 5.20 grams of aluminum oxide will be formed. One of the nice things about these stoichiometry charts is a really easy quick check is since mass is conserved, if you add up all of the grams on the reactant side and compare it to the sum of the grams on the product side, they should work out to be equal as long as nothing is going to miss with the calculator. And in this case, we get 10.89 on the reactant side and 10.90. Now, the fact that it's just a little bit off is fine. That's just due to rounding at some point. Now, if you ended up with 10.89 on the reactant side and 11 over on the product side, that means that there's a math error somewhere. So now to get the number of representative particles, you can either do each one methodically, say, all right, here's moles, and I know if I want to get out to particle plaza, I'm going to multiply by Avogadro's number, and that will give me what the result is. The thing is, since you're taking the moles and multiplying by the same number each time, it works out that the representative particles are also going to be proportional to the reaction coefficients. So that means that aluminum oxide, the number of representative particles that are present is 3.07 times 10 to the 22nd. And then for the iron metal and the aluminum metal, it'll just be 2 times that amount because they're both got a 2x value. So the iron will be 6.14 times 10 to the 22nd. Sorry about that line. I'm not sure what to do about that. And this one would also be 6.14, there we go, times 10 to the 22nd. So I think probably the longest calculation part with this will be figuring out what the molar mass is for each compound. So here I have the second chart that is on the worksheet that goes with this particular lesson. And go ahead and see if you can pause the video and see if you can figure out what some of the moles are and then find the grams for each one. And I will just wait just a second so you can pause it. All right, so I'm going to go ahead and fill in the moles and the grams. So here we have 1x for the sodium sulfate. Barium nitrate is also a 1x. Barium sulfate is a 1x. And sodium nitrate is a 2x. So that means that the molar amounts, this is the 2 reactants and barium sulfate all have a coefficient of 1. So these are all going to be 0.066, 0.066. And then the 2x, sodium nitrate, will be twice as much, which is 0.132. So remember, once we have moles and you have molar mass, you just multiply, and you can get the grams. So the grams of sodium nitrate worked out to be 11.22. Barium sulfate, once you finish filling in the molar mass, is 1540. And I'm not going to do the molar mass for you. I figured you can do that yourself. And then the sodium sulfate will be 9.37. And then let's just do our quick check. So we're going to add those two together, and you get 26.62. So 20, try to write this small, 62. And we're checking to see if it adds up to the same thing on the other side. And this time I did not have any sort of round off error, so they're exactly equal. The number of grams in is equal to the number of grams out. All right, so that's it for this particular lesson. You just need to practice a couple of times. Again, the big mistake that people make is that they get these coefficients mixed up, and they will end up with molar masses that have been multiplied by that coefficient. So if you end up with numbers that are really, really big, that's probably what's happened. All right, see you next time.